Okay, I made a slight correction. This sign here is carrying x, not t. So that's the correction. Please, it was a silly mistake. I corrected it. So we are going to differentiate u the first time. So partial u. We differentiate. Remember, we are differentiating with respect. We want to get this left hand side. Look at our target. If we are able to get the left hand side, we get the right hand side and find out that they are both the same, then we have successfully verified that this is a solution. So what you need to do is find a way to get this left hand side, get the right hand side, and see if you get the same answer. Now let's first of all get the left hand side. We differentiate first with respect to x. I believe we still remember our elementary differentiation. If we are going to differentiate this with respect to x, you see this first term does not contain any x, so it is just like a constant. Remember, if you are differentiating, if y is 4x squared and you want to differentiate y with respect to x, so if you differentiate y with respect to x, you are differentiating x. This 4 is a constant, so it comes out, you leave it, you don't touch it. I differentiate this x squared. You differentiate x squared becomes what? 2x, not so. And this becomes 4 times 2, it becomes 8x. So that is what we will do here. You see that this first one does not have any x, so it is a constant. You leave it the way it is. So this becomes e minus kt. Now, since we are differentiating with respect to this is what we will differentiate. If you differentiate sine x, you get cos x. So this is the first partial derivative. Because this is second partial derivative, we have to differentiate again. The second time, that is partial square u over partial x square. Now, if you differentiate this again with respect to x, remember this is the same thing as differentiating again with respect to x. So if you differentiate this is still a constant, you still repeat it, e minus kt. If you differentiate cosine x, you get negative sine x. I'm going to write the minus here. Then we have sine x. So this is the second partial derivative. Now this is our left hand side. Now let us find our right hand side and see if we evaluate the right hand side, it will give us the same thing as the left hand side. Now I'm going to divide this. I'm going to use this part for that. Now this is LHS, left hand side. Now let us come to the let's work on the right hand side. Remember, the right hand side, we have the first derivative with respect to t. I believe so. So we differentiate u with respect to t first. If we do that, remember this is our u is equals to t. We are not differentiating with respect to t. We have two functions here, exponential and trig. The one carrying the trig does not contain any t, so it's just like a constant, we don't touch it. This is the one we will differentiate because this is the one that carries the t. Now if you differentiate an exponential function, you differentiate the power, the exponential here, you differentiate it. When you differentiate minus kt, you differentiate minus kt. Remember, you're differentiating t, so if you differentiate t, t is 1. If you differentiate a number, you get a variable, you get just like when they say differentiate x. If you differentiate x, it will give you 1. So if you differentiate t, you will get 1. So 1 times minus k is minus k. You now write that minus k. I'm not supposed to be explaining this, but I just have to do it for those that maybe will not understand it. But for those that know what I'm doing, it's easy. So when you write minus, that is, I differentiated this power here first. Whatever I have, I use it to multiply the exponential. So minus k is what I got when I differentiated this power. I will now use and multiply the exponential. Exponential minus kt. So this is how you differentiate exponential minus kt. But remember, there is sign here. This sign we are not differentiating because it's just containing only x. Remember, our derivative is with respect to t, so we just repeat the sign the way it is. Sine x. Are you seeing this? Then the next thing is, remember there is a 1 over k in the right hand side, so we have to bring in 1 over k here. So we multiply 1 over k with partial u, partial t, so that it will look like the right hand side. Remember, our target is to get this right hand side. So if we do this, that means 1 over k is also multiplying this part. Since we are multiplying this part by 1 over k, multiply this part by also 1 over k. So we have minus k e minus kt sine x all over k. Same thing as 1 over k. K will cancel k. So we are left with minus e minus kt sine x. This is now, remember, this is the whole, this and this is the whole right hand side. This answer we got, which is our right hand side. Now you can see from the left and the right, you can see that they are the same. The left hand side and the right hand side are the same. LHS is equals to RHS, meaning that we have proved that this U is a solution to this heat equation. I believe it's very, very simple. That is that. We'll talk about it. This is the next question. It's still in the material. It says we have to verify that f of x plus kt satisfies the wave equation. This is the wave equation. Now we are going to answer that. Okay, I'm taking the whole of this. Now, solution. Now, this is looking different because look at, we have f x plus kt. It is different from f x comma k comma t. These two are different. There is a sum inside the function. So what we do in this scenario is, anytime you see something like this where there is a sum or difference inside a function, what you do is you use a single variable to represent whatever is inside the function. So I'm going to use u. Let u be equal to x plus kt. So whatever is inside, I let u to represent it. So that I will now have f of u. This is what I will now have. Not so good. I will now differentiate. Now, look at the question. The question says fxx is equals to 1 over k square ftt. I told you that anytime you are trying to verify, you are trying to show that the left hand side will give you the same thing as the right hand side. In the other example, I started with the left, not so. I first of all differentiated the first time, then I differentiated the second time, and then I did the same to the right and compared the two sides. We are going to do the same here. Now we are going to first start with the left hand side. Left hand side, what are we seeing? fxx. So we are going. This is something as I believe by now you should know how to write this in the partial form. This is something as partial f. Remember, this is x, so it's second derivative, so there will be square. Partial square f partial x square because of xx. So now I'm going to do this. I'm going to first of all, before I find the second derivative, we have to find the first derivative first, just like we did the other one. So I'm going to find. Okay. Now I'm going to do this, but there's something we should do here before we come to that. First of all, we differentiate this partial u with respect to x. If you differentiate this function with respect to x, because there is a plus here, this is a different term. If you differentiate kt, you get 0. If you differentiate x, you get 1. So this will give you 1. You also differentiate with respect to t, partial u, partial t. If you differentiate u with respect to t here, x is a constant. Because of this addition here, if you differentiate x here, is a constant is 0. If you differentiate t on this other side, if you differentiate t, you get 1. 1 times k is k. So here you get k. Now let's come back to that. Now I told you I will first find the first derivative. So we'll find fx first. Now when you see fx, you can write fx as partial f partial x. I believe we know this. Now look at fx plus kt. we let u to be x. So you see that we now I wrote something like fu. Now f is a function of u, but u itself is not a function of x and t. So this is function of a function. So it's like when you're differentiating function of a function, you use what we call chain rule. Now chain rule is easy. You are differentiating f with respect to the one that is inside u. Differentiate f with respect to x. So you have to differentiate f with respect to this one first, because this is the one that is covering x. Look at x is being covered by u. So you have to differentiate with respect to that cover first and break it down with respect to u. Then you differentiate that cover, the u, with respect to the x. Now this is chain rule. It doesn't change anything. Look at, if you look at the numerator, you have the partial u, partial, you can cancel out and we still have partial f, partial x. We are just bringing in this partial u because of we represented u with the inner function. So whenever you're applying chain rule, if you're applying chain rule, partial, now if I just pick a random example, let's say I want to find partial f, partial t, where f is a function of t plus 5y, something like this. I cannot differentiate f with respect to t direct. I have to use another function to represent this first, because this is a new function that is inside. So I can use anything. You can use maybe w. Let w be t plus 5y. So when you have used w to represent it, that is when you now differentiate f with respect to w first, partial f, partial w with respect to that w first, before you now differentiate the w with respect to your final t. So you cannot jump from f to t direct. You must move from f to a function that you represent with whatever is there before you move from that function to the required t. So before you move from w to t, this is how you use chain rule. So we are doing that now. We move from f to u, which is the intermediate, then from u to x, which is our required derivative. Now, remember, partial u, partial x is 1. We've gotten it here. So this can be written as partial f, partial u times 1, which is written as partial f, partial u. Just now, if fx is partial f, partial x, then fu, partial f, partial u will be fu. So fx is fu. So anytime I see fx, it means fu from this. Now let's look for the second derivative. We have gotten the first. Now let's look for the second one, which is the whole left hand side. Fxx is equal to, remember, this can be written as partial square f over partial x square. And then we can rewrite this as partial over partial x of partial f over. Yes, I'm going to write it that way. Now, okay, partial over partial x of partial f over partial x. Yes. Remember, this is the first derivative we got. Not so. The first derivative. Now we are differentiating that first derivative again with respect to x. That is why we have the second derivative. Look at fx is first derivative. Differentiate first derivative with respect to x again will give you second derivative. So we are differentiating first derivative with respect to x again. So if you expand this, you still get this partial square f partial x square. So these two and these two are the same. I just spread this one out so that it can be easy for us to understand what this means. Okay. So now we know this already. This is this. Now so look at partial f partial x is this. So I'm going to replace it there. We have partial over partial x into, in place of f partial x, I'm going to write this partial f over partial u over partial x. I believe you understand this. It's just a replacement. Then if I do this, now we are differentiating this. These are two different functions. Just like when you have two functions, u and v, and you want to differentiate two functions, you use product rule because the functions are multiplying each other. You keep the first one constant and you differentiate the second one, dv, plus you keep the second one constant and you differentiate the first one, v. You keep the second one constant, v, differentiate the first one, du. This is product rule. So because these two are two different functions, we are going to use product rule to differentiate it. So we'll keep this first one constant, partial f over partial u. We will now differentiate this one. If we differentiate the first with respect to x again, you get the second, partial square u over partial x square. Remember, this is a first derivative. We are differentiating it again. You have partial u, partial x. They say differentiate this one again with respect to x. That means we have partial square u, partial x square. That's what I did. Then plus, remember, product rule plus, we kept the initial one, we kept the first one constant, differentiated the second one. Now we are going to keep the second one constant. Partial u, partial x, and differentiate the first one. So if we are going to differentiate this one, remember we are differentiating, this is what we have, we are differentiating this first one, that is we are differentiating with respect to x. So this will be partial square f partial square f over partial x partial u. I believe you get it. I expanded this. Now, this one will give us 0. Do you know why? The reason is because, look at the first derivative, partial u partial x is 1. The first one. But this one is, we differentiated this first one, so if we differentiate 1, you will get 0. The second derivative is 0 because the first derivative is a constant. When you differentiate again, getting second derivative to be 0. If you differentiate 1 is 0. So that's why the 0 times anything here is 0. So this one is gone. And then on this side we have partial u partial x. This is 1 already. 1 times. Now this is partial x partial u. Partial x partial u. Now if you have 2 times 3, it's the same thing as 3 times 2, commutativity. As long as they are multiplying, no matter which one comes first, you still have the same thing. So I can write this as partial square f over partial u partial x. It's still the same thing, no matter the one I bring first. After all, they are still multiplying. So this becomes, this one is gone, so 1 is gone, so we are just left with this. So I can break this apart into partial over partial u of partial f over partial x.